Hello everyone, welcome to this session on ARM microcontroller architecture. Today we'll take a closer look at the ARM architecture, the backbone of modern microcontrollers, and see why it's so widely adopted across industries. Using the STM32 microcontroller as an example, we'll explore the CPU memory, peripherals, and other key features that make ARM-based microcontrollers so versatile. Before we begin, click on the I button or check the description for a quick introduction to embedded systems and microcontroller architecture basics. Let's get started, and remember, this is COCOWATT Media. Let's begin with a quick overview of ARM architecture. ARM stands for Advanced RISC Machine, and it's a type of processor architecture used in many microcontrollers and microprocessors. ARM processors are known for being energy efficient, high performance, and cost-effective, which makes them ideal for embedded systems like IoT devices, wearables, and industrial controllers. ARM processors are based on the reduced instruction set computing or RISC design philosophy. This means they use a small set of simple instructions that can be executed very quickly, making them faster and more efficient than processors with complex instruction sets. Now, you might be wondering, what are the other types of processor architectures available? Well, apart from ARM, there are a few other common architectures. x86U. This is the architecture used in most desktop and laptop computers. It's powerful but consumes more power, so it's not ideal for battery-powered devices. AVR, a popular architecture for small microcontrollers like those used in Arduino boards. Oryx UA, robust, safety-focused architecture, often used in automotive and industrial applications where reliability is critical. ARM is by far the most widely used architecture in microcontrollers today, and the STM32F4X is based on the ARM Cortex M4 core, which we'll explore next. Now that we've covered the basics of ARM architecture, let's dive into the CPU of the STM32F4X. The STM32 is built around the ARM Cortex-4 core. But what does that mean? Let's break it down in a way that's easy to understand, even for absolute beginners. The Cortex M4 is a 32-bit processor, meaning it can process 32 bits of data at once. This makes it faster and more powerful than older 8-bit or 16-bit processors. It's designed for high performance and low power consumption, making it perfect for IoT devices, wearables, and industrial control systems. Now, let's look at some of the standout features of the Cortex M4 core. First, the floating point unit FPU. This hardware unit handles floating point calculations like 314 or 0.001 efficiently. Without it, the CPU would rely on slower software-based calculations. For example, in an audio equalizer app, the FPU can perform real-time filtering and frequency analysis with ease. Next, the Adaptive Real-Time Accelerator (RT Accelerator). This feature allows zero-wait state execution from flash memory, meaning no delays even at 11068 MHz. For example, in real-time signal processing, this ensures lightning fast data access. Then there are the DSP instructions. These are optimized for tasks like filtering and Fourier transforms, making the STM32 ideal for audio processing, sensor data analysis, and motor control. Let's talk about performance. The ARM Cortex M4 core in the STM32 is a real powerhouse. It can achieve 210 DMIPS, which is Dristone million instruction per second at 168 MHz, with a performance of 1.25 DMIs per MHz. This means it's capable of handling complex tasks in real time, like processing sensor data or controlling motors with ease. Now, let's dive into the bus architecture. The ARM Cortex M4 core uses a Harvard architecture, which means it has separate buses for instructions and data. This allows the CPU to fetch instructions and data simultaneously, significantly improving performance. First, there's the I bus, or instruction bus. This bus fetches instructions from memory. It connects the CPU to the flash memory through the RT Accelerator, ensuring fast and efficient access to your program code. Next, we have the D bus, or data bus. This bus is responsible for fetching data from memory. It connects the CPU to SRAM and other data memory regions, allowing the CPU to read and write data quickly. Finally, there's the S's bus, or system bus. This bus is used to access peripherals and other system resources. It connects the CPU to the AHB, Advanced High Performance Bus, and APBs, and Advanced Peripheral Bus, which are used to communicate with peripherals like timers, ADCs, and communication interfaces. While speaking of buses, let's take a closer look at the AHB and APB. The AHB, or Advanced High Performance Bus, is designed for high-speed communication between the CPU memory and high-speed peripherals like the Ethernet MAC and USB OTG. It's perfect for applications that require fast data access. On the other hand, the APB, or Advanced Peripheral Bus, is a lower speed bus used for communication with low-speed peripherals like GPIOs I2C and SPI. It's simpler and more power efficient, making it ideal for peripherals that don't need high-speed data transfers. Now, let's talk about DMA, or Direct Memory Access. The STM32 includes two DMA controllers. These controllers enable fast data transfers between peripherals and memory without CPU intervention. For example, in audio streaming applications, DMA can quickly transfer large amounts of data between peripherals and memory, ensuring smooth and uninterrupted performance. Now that we've covered the CPU, let's move on to memory, the place where this STM32 stores its instructions and data. It holds everything the CPU needs to perform its tasks, from the program code to the data it's working on. Let's break it down into the different types of memory available in this microcontroller. First up, flash memory. This STM32 has up to 1 MB of flash memory, which is used to store your program code. It's connected to the CPU through the RT Accelerator, ensuring fast and efficient access to your code. Next, we have SRAM, or Static Random Access Memory. This STM32 has up to 192 KB of SRAM, which is used for temporary data storage while your program is running. Additionally, it includes 4 KB of back SRAM and 64 KB of CCMN, which is core-coupled memory, tightly coupled to the CPU for faster access. Then there's OTP memory, or one-time programmable memory. This STM32 has 512 bytes of OTP memory, which can be used to store data that should never change, like serial numbers or calibration values. Finally, this STM32 supports external memory like SRAM, PRAM, NOR, and NAND through the Flexible Static Memory Controller F, which is FSMC. This allows you to expand the memory capacity of the microcontroller, making it ideal for applications that need to store large datasets, such as high-resolution images or audio files. So, in summary, the STM32 offers a variety of memory options to store your code, data, and even large datasets. Now that we've covered memory, let's move on to the clock system, which is essential for keeping everything running smoothly. The clock system is like the heartbeat of the STM32. It provides the timing signals that synchronize all the operations inside the microcontroller. This STM32 has multiple clock sources, each with its own characteristics. First, there's the HSI, or High-Speed Internal Oscillator. This is a 16 MHz internal oscillator with a precision of 1%. It's a good backup clock source when higher accuracy is needed. Next, we have the HSE, or High-Speed External Oscillator. This is an external crystal oscillator with a frequency range of 4 to 26 MHz. It offers very high precision, 0.11%, but has a longer startup time. Then there's the PLL, or Phase Locked Loop. The PLL can multiply the frequency of other clock sources to generate higher frequencies up to 168 MHz. For low-power applications, this STM32 includes the LSI, or Low-Speed Internal Oscillator, which runs at 32 kHz. There's also the LSE, or Low-Speed External Oscillator, which uses an external 32 kHz crystal. This is often used for the real-time clock RTC and other timing-critical tasks. Let's move on to peripherals. Peripherals are like the senses and muscles of the STM32. They allow the microcontroller to communicate, measure, and control things in the real world. Let's take a look at some of the key peripherals. The STM32's GPIOs are highly configurable. They can be set as outputs with push-pull or open drain, or as inputs with floating or pull-up or pull-down resistors. Most GPIO pins can also be configured for digital or analog peripheral functions. With high current capability, they support high-speed toggling up to 84 MHz. Plus, the I/O configuration locking feature prevents accidental changes to GPIO configurations. This STM32 has 3 12-bit ADCs, each supporting up to 16 external channels. It offers multiple modes of operation, including single-shot mode for converting one channel at a time, and scan mode for automatically converting a group of selected channels. And Watchdog is available for monitoring specific analog channels. It supports DMA for efficient data transfer and timer synchronization for precise timing. The STM32 features 2 12-bit DC that convert digital signals into analog voltage outputs. Key features include synchronized update capability, noise and triangular wave generation. This supports DMA for efficient data transfer and external triggers for synchronized output. This STM32 has 3 types of timers. Advanced control timers offer 16-bit resolution, up or down counting modes, and complementary WM outputs with programmable dead time insertion, ideal for motor control. General purpose timer supports 16-bit or 32-bit resolution with DMA and max clock speeds of 84 MHz or 168 MHz. Basic timers are used for DAC triggering and simple time-based tasks. This STM32 includes 2 Watchdog timers for system reliability, an independent Watchdog 12-bit down counter clocked by a 32 kHz internal RC oscillator operating in stop and standby modes, a window Watchdog 7-bit down counter with early warning interrupt capability clocked by the main system clock. This STM32 includes a 24-bit sys-tick timer, primarily used in real-time operating systems RTOS. It features auto-reload capability, a maskable system interrupt, and a programmable clock source. This typically used for RTOS task scheduling and time measurement. Now that we've covered some peripherals, let's move on to the communication interfaces, which allow the STM32 to interact with other microcontrollers and devices. This STM32 has 6 USART and UART interfaces supporting asynchronous and synchronous communication. It also supports LIN, IRDA, and smart card mode, with max baud rates of 10.5 megabits per second for USART and 5.25 megabits per second for others. With 3 I2C interfaces, this STM32 supports multi-master and slave modes. This is capable of speeds up to 400 kHz in fast mode. This STM32 has 3 SPI interfaces, supporting full duplex and simplex modes with speeds up to 42 megabits per second. It includes CRC support and DMA integration. This STM32 features two RTOS interfaces designed for audio applications. It supports sampling rates up to 92 kHz with 16 and 2-bit resolution and precise clocking via PLI2S. This STM32 includes an SDIO interface for high-speed data transfer with SDIO and MC cards at up to 48 MHz. With two CAN interfaces, this STM32 supports CAN 2.0A and 2.0B standards at speeds up to 1 megabits per second. This STM32 supports full speed of 12 megabits per second and high speed of 480 megabits per second USB communication. It operates in both host and device modes. It also supports 10 to 100 megabits per second of Ethernet with dedicated DMA and IEEE 1588 for time synchronization. This STM32 communication interfaces cover a wide range of applications, from basic serial communication to high-speed networking. With features like DMA support, CRC verification, and protocol compatibility, it's a reliable and powerful choice for industries. Now that we've covered the communication interfaces, let's move on to the safety and security features, which are essential for building reliable and secure systems. In today's connected world, ensuring the integrity and safety of your applications is more important than ever. This STM32 is equipped with several features to help you achieve this. This STM32 includes a hardware-based CRC cyclic redundancy check unit. This unit ensures data integrity by detecting errors in communication protocols like CAN or Ethernet. This STM32 features a real-time clock with tamper detection. This allows the system to detect and respond to unauthorized access attempts. This STM32 includes read or write protection for memory blocks, ensuring that critical data cannot be accidentally or maliciously modified. This STM32 includes debug port protection, which prevents unauthorized access to the microcontroller through the debugging interface. That's a wrap on today's exploration of the STM32 microcontroller architecture. We've covered the powerful ARM Cortex M4 core, its key features like the floating point unit, UART accelerator, and DSP instructions, as well as the memory architecture, clock system, and peripherals that make this microcontroller so versatile. If you found this video helpful, please give it a thumbs up. Subscribe to COCOWATT Media for more engaging tech content, and don't forget to share it with others who might find it useful. Let's keep learning and building amazing things together. See you in the next one.